Welcome to the presentation on FlexibleIP, or FIP. I'm Colin O'Flynn, and this presentation was originally given as part of IEEE GreenCom. This was just a slide showing where I'm at Dalhousie University in Canada. And in this presentation, I'll talk a bit about cross-layer design motivation and why we care about cross-layer design in low-power networks and low-power stacks, running IPv6 on small devices. And then I'll get into FIP, where it came from, the goals, the structure, as well as a quick demo. So cross-layer design is when we sort of want information about layers that wouldn't normally interact. And why we might care about this, especially with low-power devices, is stuff like, for example, if we have the timing information from a lower layer, we could use that as part of a synchronization protocol. So at a higher layer, at the application, we want several devices to be synchronized. But to get that sort of synchronization, it's easier if we can know, for example, at the physical layer, when did the radio first start receiving this particular frame. Most radios provide you with something like a starter frame interrupt, and you could use that if you somehow had access to the data. In a classical method where everything's nicely layered, you may not have that access. So what you end up doing is sort of introducing hacks into the code. And as you add more protocols, there gets to be more hacks, and this becomes sort of really unwieldy. So other stuff you might want is when you're sending a message, it may be useful to tell the radio, ignore your normal carrier sense multiple access collision avoidance routines, which listens to the media, and if the media is busy, don't transmit. You want to override that and say if the media is busy for too long, give up. Normally it would wait further, but give up because that packet's no longer really that useful because the timestamp I put in it at the application layer won't be as valid. So I want to send specific messages to the lower layer or disable automatic retries. If it doesn't make it through one time, stop. Come back to me and I'll give you a new message. There's lots of protocols that try to get the address information. Either when you transmit a packet, you want to manipulate the lower layer addresses, or you need the lower layer addresses. And we'll see this in 6LoWPAN later. LQI, or link quality information for wireless links, is always very useful, as is the receive signal strength indicator, or RSSI. And these can tell you things about when you have a routing protocol, what links are more reliable than others. If it's a negotiated link, think Ethernet, for example, we can have Ethernet 10, Ethernet 100, or Ethernet 1000, or even beyond now. And similar protocols, you may have one type of physical layer, but it could be running at different speeds. So your routing protocol, you want to know what speed am I actually running at. And again, you'll see this in wireless. You'll have some idea, how busy is a particular area or channel. Maybe I can't send messages as quickly through one link as I can another. For security, you may want to know on a frame-by-frame basis if a frame was received with security or not. Often, when you use security in these networks, you just have a mandate that every node has to use security. If you receive a frame that's insecure, you just dump it completely. The risk is that sometimes it's hard to know at higher layers, was this frame originally received secured or not? Because obviously that can make a huge difference in what the frame is allowed to do. But it can be useful to have this ability to receive unsecure and secure frames because, maybe certain devices don't have the ability to process security, or certain devices you don't want to have the hassle of giving security keys to. So if there's a way to not just globally enable or disable security, but on a frame-by-frame basis know, was this packet received with security or not? That can be very useful in cross-layer design. Another aspect of low-power devices that's interesting is hardware acceleration. So hardware accelerating is where we sort of design some specific hardware to go with our processor. Things like the header processing we could put into hardware. The checksum calculations, that's very easy to put into hardware. And most of these IP stacks are spending a lot of time doing table lookups. They're looking up things in routing tables. They're looking up things in neighbor tables. So if you optimize that a bit, you can see some pretty good improvements in your speed. And the idea here is often that we want to get improvements in speed because then the processor can spend more time asleep. So for doing these sort of experiments, it's useful to compile on something like a FPGA with microblaze or other soft core processors. So why do we want IPv6 on small devices? There's lots of advantages to it. One of the most important is IP is end-to-end, so that means you have a wireless network and you can access it just from your desktop computer or a computer across the world. There's no tricky translations performed anywhere. You're just sending IP packets to an end device. You're sending UDP or whatever else you want to use. So it's much more scalable and much easier to use. In particular, we like IPv6 because the addresses are so much bigger. So here we have a slide that shows the IPv6 header, and these source and destination addresses are each 128 bits. This means every device can receive an address that's totally unique to it, and no one else in the world can have it. This is unlike IPv4, where the space just isn't big enough to do this. It also works out there's a lot of other efficiency we can gain, because you can do stuff like have groups of devices easily assigned to certain types of addresses. So the beginning several bits can mean a certain address, a certain subnet. And there's a lot more you can sort of learn about with IPv6 if you go into it. So the IPv6 header, when we send it over these low-power devices, is pretty long. It's 40 bytes long. If we talk about IEEE 802.15.4, which is what's used in Zigbee and a lot of these low-power sensor networks, you have a maximum total size of that frame of 127 bytes, so that seems crazy. The header alone is filling up most of it. But as it turns out, we can compress the header, and there's something called 6LoWPAN, and you can reference the RFC to see the details. But basically what we do is we look at stuff like the version number is constant, the traffic class and flow label are often one of a few values. The payload length you can calculate based on the received header. The next header is, again, often constant, one of a few values, and so forth. And the addresses obviously make up the bulk of this header, but the trick we use here is that most of the time with IPv6, or at least in these networks, we're using addresses that are derived from the MAC address. The MAC address is the unique address assigned to every device. In 802.15.4, we could call that the extended address, which is sent over the air to send, I want to send a message to this guy, so I'm using addressing to send it to him. So at the receiver, we already know the address of the sender and the address of the receiver, that's us, that the IP addresses are probably based on. So we just have a few flags to say if this is the case or not. And you just don't even transmit the addresses at all then. What this means is that you basically are sending a few flags in 2 or 3 bytes, and you may need a few bytes of inline header fields, so these are fields that are not the default or most common values. Either way, though, we're drastically reducing the size, and you can see it makes a lot of sense then to send IPv6 over these networks because there's very little overhead here. And we still get all those advantages of, end-to-end, and it's easy to use, easy to understand, and all that. So there is other IPv6 stacks up here. Why does FIP matter? Why do you care about FIP? Am I reinventing the wheel? And that's a good question. My personal background, I helped as a member of the team that released Micro IPv6, the stack in Kentucky. There's a stack by Atmel that includes a tiny IPv6 stack. I call it a hack stack here because it was actually designed to be very, very small. So small it wouldn't pass all the IPv6 testing. It was designed to be something that worked, but it was written with such strong optimizations it was really hard to extend beyond that because it was designed to fit, inside of a 32K device. And you could even do stuff like upload a new firmware image using TFTP to the device and it would boot it. And that's all within that space. So it's tiny, tiny stack. And it also helped developing some IPv6 stacks for industrial protocols. So the downside, what I sort of saw from all this, is that a lot of stacks are written to be small and they accomplish that goal very well. Kentucky's a good example. It's small, it's fast, it can run on tons of different devices. And the only downside of it is that because it's been written to be small, it had to have some sort of optimizations in the source. And you see stuff, for example, the main UIP process function here that you sort of would have to modify if you want to make changes add some new protocol you've invented, is pretty big. We're talking about 1,300 lines. So there's a lot of code to go through. And we'll see sort of in other stacks, you run into similar problems, that it's either very big or it's been designed with sort of one way of doing things in mind. So what I really aim for with FlexibleIP is that the flexibility and code readability, those are the primary goals. It is designed to be small, but that's not the be-all, end-all of it. When I say small, I still mean it'll fit on, a 64K device, 64 kilobytes of flash, which isn't nearly as small as Kentucky would fit on, but it's pretty small, and I'll show later sort of why we care about that. It's also designed to be deployed on different devices, so natively it supports, an 8-bit micro, but you can also support a 32-bit micro, so it has the option, to add all the needed flags you need for packing structs and things like that. So there's a few things to always consider when you want to deploy on a 32-bit device. It also compiles on the PC for ease of development, and I'll demo that later. So I mentioned this idea of how small we want to go, and why I chose this sort of idea of not caring too much about code size is right now, these are prices as of yesterday in Canadian dollars. So here we have a ATmega 128 RFA1. And this device has 16K of flash. So let's see if I can get it. No, I don't. So 16K of 16K of SRAM and 128K of flash. So it's fairly big. And you can see it's about $5.66 in quantity 100. And this device has the radio and micro controller all integrated inside it. By comparison, if you want a smaller device, you would have to buy a separate microcontroller and a separate radio, and then combine them. But when you look at the cost of this, and this is 32K of flash, so much smaller, you look at the cost of this, and you're not saving that much money. If you buy them together, you do get a bit of a discount for certain devices. But again, the point is that, especially for development, maybe you're saving $1, which would never matter for development, and most of the time development boards are using these bigger devices anyway. You can also buy a number from other manufacturers. There's nice ARM devices, ARM with integrated 15.4 controllers. And again, there's no real point to optimize this IPv6 stack to sort of the end of the earth, because economically it's not that important. The second thing is the compilers are pretty good. If you give them well-structured code, it might not be as good as the optimized code you produce, but it's still pretty good. And the trade-off here is the development's a lot easier. When I was going through and creating FIP, I was careful to make sure, test, okay, if I want to do different things, will the compiler optimize that out? So here I'm testing, and you don't see the previous one without a struct, but I'm using a struct with a buff here, and you can see that buff is just declared. And I said, well, for a statically allocated buffer on a small device, I might want to use something like this. But if I want to support dynamic buffers, I'm going to need to use pointers instead. But you notice if I use a pointer, and I use it in the same format as buff, the compiler is fine with that, and I initialize it to point to the buffer, the compiler doesn't care. It makes that basically just as efficient as if I had used the buff directly. And we see here I'm using a pointer with a buffer with an offset, and again, it's still basically the same. So the point is the compiler is so good, it recognizes what you can do. So you can write code that is flexible. For example, use pointers so that with dynamic buffers you can easily point to different buffers. But it'll realize when you just have one buffer, and it'll sort of optimize that away. The other thing I wanted to get rid of is the fact that many of these other IPv6 stacks also include operating systems in them. So something like Kentucky or TinyOS have their own OS, which is great if you want a complete solution. If you already have something working and you just want to add an IPv6 stack, or you just want to experiment with the IPv6 stack, this can be more complicated. So here's the host interface, as I call it. All FIP needs, FIP runs in a loop, so you just need to call this one process ever so often. And it'll call back to the host some functions to get time, and it uses that timing information for changing states and expiring things. But that's basically all you have to provide. Obviously, there's some interface functions for sending and receiving packets. Those are also very simple, though. The idea is to make it easy to integrate with any OS, or even run on bare hardware. So architecturally, how FIP looks is it has this idea of a packet buffer. The packet buffer includes a lot of different stuff. So the first thing it has is it has these buffers for different parts of the message. So the header, link layer headers, IPv6 headers, extension headers, UDP headers, etc. So there's a number of different buffers that can be used for different purposes. It also has information that follows that buffer. So the whole packet buffer contains more than just the data. It contains all this metadata. One of the important ones is the state of the packet buffer. So here we have the state of IP processing. As I mentioned, FIP gets called in a loop. So it uses this state to track what's happening to each packet. For example, if we're receiving a fragmented packet, and this can be at the L2, the link layer, or at the IP layer, we can set the state of this packet is IP or link layer fragmentation in process. So FIP knows that we're waiting for more fragments to arrive. And this makes fragmentation really easy because it'll just keep skipping, doing further processing on this packet. And when you get a new fragment, you can just look through all of the packet buffers, if you have multiple, that are in this waiting for fragment state, and you can say, oh, this is the one I want, add the fragment, check if it's complete or not. If it is, you set the state to now IP packet either ready to be processed or, whichever, depending if it's link layer or IP layer. We also record a few simple things like the source and destination, and for IPv6 we have some additional flags to make comparisons easy, like is this on link, is it my solicited address. So there's a number of comparisons that will be tested a whole bunch of times. If you do the comparison each time, it wastes a bit of time because you're testing 16 bytes, so FIP tries to optimize that a tiny bit by adding flags to it to say this is the type of packet we have, and you can just test the flag. It also has this Scratchpad, which we'll talk about later, and the Scratchpad is a collection of bytes that just follow this packet through its whole lifetime. So the buffer, as I mentioned, we use structs extensively, so this is to make debugging sort of as easy as possible, and we see some of those previous things I talked about here. We can either support statically allocated single use, so this is one buffer for the whole FIP. So this is on very small devices, you just have one buffer, it can process one packet at a time. You may have statically allocated still one buffer, but it can, in that buffer it can store a few small packets. This is not done yet, so this one is done, and dynamically allocated using malloc is done and tested. So the buffer type, when you change the type of buffer, it changes, there's some macros to access the buffer, and the actual source file that deals with allocating new ones changes. I mentioned the Scratchpad. The Scratchpad is how we deal with some of these cross-layer issues. So the Scratchpad is a collection of bytes that will follow this specific packet, and the user, to some degree, can decide what goes in it. You can coordinate this across different layers. So at minimum, what we use it for is example, 6-LOWPAN link layer fragmentation. While that's occurring, there's a number of information that needs to be stored about this packet. So for example, we have how many bytes we've received, how many were expected, is this the first fragment or not, when does it expire, because we want to time out if we don't get everything. And normally what you'd have to do is, allocate a new buffer, maybe with malloc, and somehow associate this with the packet, maybe with a pointer. This has some potential problems, A, because now we need malloc, or now we need the other layers to create their own buffers, and 2, it's fairly easy to, for a bug to not free part of this, and now you have a memory leak. On an embedded system, this is terrible. So to avoid that, every layer can just use the Scratchpad. So at the 6-LOWPAN layer, when we're doing the 6-LOWPAN processing, it has control of this Scratchpad. So it defines what goes in the Scratchpad as this structure and just uses those bytes. Once it's out of the 6-LOWPAN layer, 6-LOWPAN doesn't need this anymore, so it gets reused as something else. And you can actually use the Scratchpad to pass messages between layers because, for example, at the next layer after 6-LOWPAN, you can keep this information, or you could define some extra information that goes in it, and you could use that to help pass messages. It's important that because this Scratchpad is always associated with the IPv6 packet, it makes it a lot easier to deal with the problem of how do we do cross-layer, but doing cross-layer ensuring that we don't have these hacks where you have to, call back to a lower layer and say, hey, the last packet you received was security enabled, because that might be wrong because maybe another packet's coming in. So this way it's really easy. You can just, set up flags that always follow that packet. And at the highest layer, you can still get information that was inserted at a lower layer if you want. So the other thing cross-layer protocols might need is you need sort of drastic changes or access to very low core data structures. So 6LoWPAN ND is one example, and it has this line that the neighbor cache entry maintenance is done slightly differently than normally. So this line can cause a whole world of headache because the neighbor cache entry management is a core part of the protocols. So how we deal with that in FIP is that on each interface there's various periodic stuff that's done. So in this case we have this ND6 periodic unicast, and then this function is doing the neighbor cache maintenance. All we do is we have a flag that says, hey, are we using 6LoWPAN ND? If so, pass it off to this other function. And this avoids polluting the source code with all sorts of, if-defs throughout the whole thing, saying, oh, if we're using 6LoWPAN, then in this case the neighbor cache table moves like this. We just have one whole function that all passes it off to, and you can just get rid of all the 6LoWPAN ND code if you want, just by disabling that one function call. Some other features, it natively supports multiple PHY or MAC layer addresses, so 802.15.4, you can have a 16-bit or 64-bit address. And it's the same interface. It's not a separate interface. It's the exact same interface. This can be problematic in other IPv6 stacks to deal with, because that's not something they've really had before. So you either have to do something like have multiple interfaces, and it's physically the same interface, but it logically looks different depending on if it's long or short addresses, or whether you have to hack the stack somehow. This way, FIP can natively decide, there's two addresses, that's fine. When it receives a packet, it's always associated with this one interface. And when you send a packet, there's some logic to decide, which, based on the IPv6 address we're sending from, which source address to use, or you can override that, of course. But natively it supports this. It has some very good built-in debug and trace support, so frequently, code will have trace just to print to a serial port or something. Rather than that, there's a trace statement, and it can either print to a serial port or print to the screen like normal, but it's defined in such a way that you can just send a token. And this is done because then you don't waste loads of memory storing all your strings in Flash, and you don't waste time on the serial port sending all these strings. It also has some macros to easily add. Here I want to add a variable to it, so I'm saying add this variable for level error, so it comes up as an error. The variable itself, and the type of representation. So we can print IPv6 addresses, we can print integers, and they'll come up nicely formatted on the screen, and you'll see the name of the variable, and you can even see where that occurred. So I'll show that later. As I mentioned, there's documentation is important, so there's lots of documentation in Dioxygen, and in the source itself. Verification static analysis is used with Gimple PCLint. So this sort of checks for stuff like buffer overflows and doing stupid stuff, you passing the wrong type of variables to functions. And dynamic testing is done. It's with IPv6 Ready logo testing. So this extensively verifies the operation of the stack by sending, for example, all the types of, I'm sending neighbor advertisements and with all the different flag options. So this is different from just creating an IPv6 stack and say, oh, hey, it works with my computer and works with a bunch of devices, seems good. There's lots of stuff that doesn't happen in normal operation, and it's important to make sure you've still implemented that correctly, because it will happen eventually, or it could happen eventually. And if you don't process that according to the standards, you could see failures that you wouldn't see even if you do a lot of testing. So by saying it's IPv6 ready, what I'm saying is that you can look at a list of all the RRCs and all the parts of the RRC it's been tested to comply with completely. So this is a bit different from when you compare code sizes. If it's just a hack stack or something, it might not have all these options. So to get this, for example, there's an option to enable IPv6 fragment recovery, so doing fragmentation at the IPv6 layer, which FIP supports. And again, a lot of other small IPv6 stacks won't have that. Kentucky, it's worth noting, did pass at one point this IPv6 Ready testing. I don't know if it's been kept up to date or not, but it, at some point has had all these features as well. So if we look at implementation sizes, I mentioned there's a few architectures you can run it on. So here I have an AVR 8-bit, one interface, just a 6-LoWPAN, 32.8K of ROM, and around 3.4K of RAM. So pretty small. Again, the idea that a 64K device, you could fit this on with some other code, and maybe 8K of RAM would be nice to give you some headroom. But you can also, even with two interfaces, it doesn't make a massive difference. So here we have an Ethernet and a 6-LoWPAN interface. There's some extra RAM to store other data structures. SAM3, so this is a Cortex M3 part. Again, pretty good sizes. And with the Cortex M3, we can, of course, use dynamic memory, which means these memory fingers, they no longer have the IPv6 packet buffer in them. I mentioned the Xilinx microarray, so compile it on the FPGA targets, and then you can sort of also see some reasonable code sizes. And for that, that would be really good if you want to test hardware acceleration. Speed test, this is just showing you if I process a UDP packet or send a UDP packet, how long does it take in clock cycles on the AVR at each layer. So the total FIP is, I think, about 20% worse. As I've said, it's not designed to be the smallest or the absolute fastest, but it's still quite good. And when you consider in actual time what that means for a 6-LoWPAN stack, for example, that's a few bytes of the 802.15.4 over-the-air data. And there is a few differences here compared to what Kentucky and what FIP are calling UDP. So you notice, for example, that in Kentucky the UDP processing time is tiny. In FIP it's huge. Some of the UDP processing is actually done here in this measurement, but it's hard to draw a really perfect line in the sand. So you could also probably optimize this a bit. I haven't looked too much at really pushing it down. So let's see what FIP looks like. And as I mentioned, it compiles on the PC. So what I can do is get rid of this, and I'm going to pull up two command windows here. And oops, I need to find the other one. So if I have another command window here, and I just have to go to where FIP is kept. So what I'm going to do is I'm going to run FIP on my computer as it's called the simulator build. And to demo it, I also have Wireshark here. So Wireshark is listening on the loopback interface, and if I start one instance of FIP here, this has 6-LoWPAN ND code enabled, so you won't see these neighbor solicitations actually sent over the air, so we see a router solicitation. So it's going to start looking for frames. And we can see this trace functionality. So here, it's automatically added the function name that's caused this trace to occur, and then when I add those variables, it just prints them nicely. So this is just a command like that, add var, and then just command the variable name and IP, and it automatically formats it nicely for you. And it does stuff like if you're sending this in token form, it'll send that variable in binary. So it won't actually do the printf on the AVR, for example. It just sends it over in binary. And on the computer side, you can process that. Again, the point is, don't waste the code doing all that on the microcontroller, and don't waste the time sending those ASCII datas when you don't really care. You just have a program on your computer that processes it. So here we have FIP gives you some different commands. So for example, what I'm going to do now is I'm going to add a prefix. So I'm going to add AAA and prefix add length of 64, and it's going to be on the WPAN device. So we can see the device is auto-configured its own address. What I now need to do is tell it to advertise that prefix. Oops, a little typo there. So now it'll start advertising that one. And finally, I'm going to turn routing on this interface, as I believe it's off. And you can sort of So we can see the two links there. So WPAN, and this is claiming to have the Ethernet. The Ethernet isn't set up to actually send over the physical Ethernet right now. So I'm going to turn routing on the WPAN. So now what I'm going to do is clear Wireshark here, and let's the second FIP. And again, this is just sort of on the computer, so it's pretty easy. Oops. So if I just type sim, so this is going to start up another one. And we see the router solicitation from this guy, and we see a router advertisement sent back from the second one, and then this one's auto-configured an address. So you can see it says moving address. So if we look at, for example, the router advertisement, in Wireshark you can see it's actually simulating the 802.15.4 layer, simulating a 6-LowPan layer, and finally we have the IP layer. So we can see here the router advertisement and the prefix information. So that's how we run FIP on the computer, which makes it a lot easier to sort of play with and get to know. So what's still needed is TCP code, which on these low-power networks, a lot of work is done with UDP anyway, so that's why there was a big focus on it. Adding higher layer protocols and routing protocols would be handy. Again, you might be able to pull these in from other sources using, there's Ripple and TinyOS, and there's Ripple and Contiki, for example, and similar co-op implementations are available elsewhere. So there's a link to the source. You should be able to see that in the comments or on the newae.com website. So hopefully this gave you a good background on what FIP is.